So let's start. I want to wish you a warm welcome to our conference here. It's the 6th time we run this conference on system and software safety. And we will have some of you here for 2 days, and we will have a mix of activities going on. My name is Nicolas Martin Vivaldi from Adalot, and I will, together with Martin Törngren, have a few words before we start. See if this works. So if you didn't miss it, last year Stefan showed off, and I wasn't sure that he's going to bring his hockey shirt on. So for those that didn't see it, yes, it was a second time in a row World Cup final victory yesterday. But let's leave it at that. So why do we run this conference then? We do this together with KTH and ICAS, and the goal is here to have a lot of people meet and get inspiration from different domains, and also to network. So that's why we want you in the breaks to hook up with people that you haven't met from different domains and exchange ideas. To make this happen, we also want to thank our program committee that has helped us with selecting the contributions and identifying good speakers. So several of you are here today, so thank you all. Briefly about us at Adalot. So we are a consultancy company with experience in helping companies become more efficient, looking into how can we drive improvements to become more cost effective, delivering more value to their customers. So we work in different domains, work with process improvement, look into supply management situations, identifying product quality, also then functional safety, and also started to look into security development, and also open source are an area that we work with. We've been around for several years, so there's been several clients passing by. Martin, a few words from your side.
Yes. Okay, ladies and gentlemen, good morning. My name is Martin Törngren, and I would also like to wish you very welcome. Just a few words. So we have now been running this conference for 6 years, and I believe it's getting more and more relevant. We are today letting the robots out of their cages. We are putting autonomous cars on their streets, smart connected systems. So much more unconstrained environments than safety engineering normally has been dealing with. And to deal with that, we already today have complex systems, and we are adding new capabilities to them, posing challenges for safety engineering. So over the decades, the centuries, humankind has always been able to master new levels of complexity. We gain new knowledge, new methods, new tools. But today we are getting we need such an amount of knowledge that we need a lot of collaborating experts. This is a view of KTH. Different experts involved, fragmented over departments, and so on. So this really, I think, motivates this conference to get the different domains and disciplines together. We need this kind of collaboration. This is also something that permeates the idea of the ISIS competence network, where we talk about creating an ecosystem involving industry, different domains, and academia to deal with the future complex software-intensive systems. And we are in ISIS, we are working with challenges that are common across domains. That has a lot to do with the increasing complexity, lifecycle connectivity, different aspects of trustworthiness, such as safety and security. So, apart from gathering the industrial domains and focusing on the common concerns, the network has a role to provide competence and act as a catalyst to get new collaborations going. Actually, our network is this year celebrating its 10th year anniversary, and the role has really been strengthened. So the competence network collaborates with other networks. We serve students, faculty, and industry. And this year we will be celebrating our, we will have an anniversary conference in the fall. Details to be announced soon. We also have a cybersecurity and privacy event conference and summer school, which we are co-organizing this summer. So, thank you very much for attending. I think we have a very interesting program ahead of us.
So some practicalities before we go on. Yeah, a little bit of who is here. One of the ideas that we have had for the conference is to have a good mix from the different areas of industry, academia, and consulting. And the mix is still as good as we have had for all of the years, with a mix of a good spread. And if you look into the different segments, you will see that automotive is still the largest area, even though we started in Gothenburg, but those years we didn't get that much automotive. We get more or less as much automotive when we're here. And a good spread from the different domains. For the program, I mean, we will soon kick off with the first keynote. But as you see, we have the breaks and lunch, which will be up outside, just outside. And we will end around 5 today. And tomorrow, it starts already at 8:30. And for those of you, there is this still possibility to do some swapping, I guess, if you realize that, oh, I should have changed. Just come to talk to some of us if you want to do that. And in the Frontiers of Safety, I just want to highlight that we have some researchers that would like to also present some of their ideas. We have posted some of those up on the pillar, so please have a look. And Narges, she's up there. So if you want to talk to her, she's there. And Sulkarnia, was that correctly pronounced? Yes. Yes, we have him here. So those two are the ones to talk to if you want to know who wrote those IDs on the pillar out there. Conference evaluation. It's important for us to get your feedback. So we've changed a little bit this year, so because some people are only here the first day and don't hand in their conference evaluation then the second day. So this year you will have one evaluation the first day and a second one for tomorrow. So before you leave, we want your feedback. Some of the practicalities. Exits, there is on front and the back. So if something, if probably not needed, but for safety reasons. We already mentioned the coffee breaks and the lunch will be served. The coffee just up, and in the restaurants you will have the lunch and dinner. Yeah, we already mentioned the workshops. So for the moderators, if you, the presenters, want to get in touch with the moderators, I will be moderating the Frontiers in Safety and Workshop 3. And Fredrik Asplund, where do we have Fredrik? There you have Fredrik for Workshop 2. And Martin you have seen. And for the training, if you have any questions regarding the training, talk to Magnus. So I guess that's all. We want to, again, welcome you all to these 2 days. And Martin, are you going to be moderating, sharing the first half? So, yes. So if you present Peter, and yeah, fine.
Thank you, Nicholas. So let's get started. Well, that's not exactly. Whoa. Okay. So this is probably suitable for a safety conference. So it is my great pleasure to introduce Peter Larkin, our first keynote speaker.
Thank you.
Peter has a long experience from both academia and industrial practice for safety engineering. And you are going to tell us what should be in the safety standards.
I hope so.
Understand correctly. We very much look forward to your talk.
Thank you, Martin. Good morning, everybody. So this is about assurance points. That is a technical term that I invented. We'll see what it means in a bit. First of all, I'd like to say why standards are important. Standards are important for engineering They originally came because of telecommunications. Morse code was the first standard. You translate speech into signals. Your other person at the other end needs to be able to translate those signals back into speech. So it has to be understood at both ends how that is done. Thus, you have a standard. Morse code was the first one. The internet is one of the latest ones. We've got another issue at the moment with electric cars in Europe. You need to connect cars to chargers at both ends of your journey. If those journeys are going to be in different countries, then you need standards between the countries to charge those, to form the connectors to charge those cars. And that's been done by Germans, mostly Mennekes and Daimler. Methodological standards are also important. Industrial safety critical equipment is often available as components. And those components are supplied by manufacturers that supply those components to all kinds of people all over the world. It's a very good idea if those components can be designed and assessed to a uniform, agreed set of criteria. And so methodological standards are very important. The basic safety standard for safety is IEC 61508. That is for safety concerning systems which are operated by digital equipment. So electric, electronic, programmable electronic is the word for all of that, or EEPE. It doesn't apply to aerospace. They've got their own. It doesn't apply to medical systems. They've got their own. It is required for industrial process plant. Industrial process plant has its own safety standard, 61511, and they explicitly refer to 61508 Part 3, which is the software part for software. So the software that is designed for industrial process plants must also conform to 61508-3. It's been adapted for rail, for protection systems, and also for onboard control systems for rail. That's in a separate series of standards from Senelec. And it's been adapted for road vehicles through the International Standardization Organization, ISO. Now, I'm going to talk about cybersecurity. We do have a problem with cybersecurity. Current events include penetration of various critical systems with hostile intent, with apparently criminal intent, and also sometimes as proof of concept. Two people in the US took over control of a Jeep theoretically being driven by a journalist a few years ago that made the headlines. It was certainly possible. The reason cybersecurity is important, we will see in a minute. But let's look at what the current standard says about cybersecurity. This is 61508 Part 1. That's the general systems part. It says, if the hazard analysis identifies something as a security threat, then you should perform a security threats analysis. I've put that in boldface. And you should carry out a security risks analysis. And if security threats have been identified, then you should carry out a vulnerability analysis. Does everybody know what any of those are? None of those terms are defined. None. Zero. Nothing. They're not even in common use. You can't refer to what engineers do. And more importantly, nothing actually says you have to do anything about it. You just have to carry out a security threats analysis. So what do? Call your local security firm that is good with locks and keys and building security and say, here's a document, give us a report. Then you've performed a security analysis or a vulnerability analysis or a security threats analysis or whatever it is. And then you're done. You don't actually have to do anything about it. And the current edition of the standard, which says all of this, is going to be valid at least until 2020. More likely 2022 is when the new edition is likely to come out. There's a little more in the process plant standard, because that's a little later. The last edition of that was written in 2016, which is only a couple of years ago. They say you have to perform access control. There's about 2 pages total on what you need to do to perform access control on which parts of the system. it doesn't say how you are to perform access control, just you are to do it. So let me give an example. You have protected your control system. Your control system runs on one of these operating systems where there is an administrator password or a root password or a password that gives you access to do anything. First of all, it's password controlled. Almost everybody knows that simply having a password control would be no good, but never mind, let's just say it's password control. And because we're dealing with engineers and operators and people who've been trained who are not particularly cybersecurity experts, this password is written on a post-it note and is put on every screen that an operator has access to in the control room. And that is access control, isn't it? It's not very effective, but it is control, and it is control of access. And that's all that 61511 requires you to do. Imagine if that were a nuclear power station. Am I going on the right way? No, I'm not going on the right way. There I'm going on the right way. So why am I mentioning cybersecurity? I've started on with safety, and I'm now talking about cybersecurity. Why? Because the safety standards are predicated upon the fact that if you have unwelcome inputs that are going to cause your system to break, and this break to cause damage, those unwelcome inputs are fairly rare and are given to you by nature or by circumstance. They're essentially stochastic. You've seen all the common things already in your preparation and design of the system, and you're really worried about the uncommon things that come along that you haven't thought about, and you're assuming those are stochastic. That is, if they haven't come along in your design and building of the system, they're not likely to have come along in operation of the system all that often. And this is a stochastic nature, likely. How often do these things occur? With cybersecurity, this is very different. They don't occur at all. Then somebody discovers something, it's called a zero-day exploit, if they design an exploit for it. And then all of a sudden, if the exploit is feasible, you go from having nothing to worry about to being constantly dealing with these inputs that are going to trigger potentially unsafe situations. It's not at all stochastic. It's exactly the opposite of stochastic. So it's never and then often. And some of my colleagues have pointed out that this means that cybersecurity is a game changer for safety or for systems which have safety sensibilities and which need protection. Now, the first exercise, spot the cybersecurity vulnerability. I'm not carrying a phone, I don't carry a phone, so where's the cybersecurity vulnerability? Right in there. That's the cybersecurity vulnerability. It's still the case that most cybersecurity exploits, about 70% of them, actually require human beings not to do something or to do something in order that things are exploited. The person is still the most important part. Thankfully, that may not last long. So I'm talking about improving standards. Let's talk about what's been said about improving stuff in the past. In the 1980s, Barry Beam, when he was head of DARPA for a while, was reputed to have said about formal methods simply that they don't work. Many people, including colleagues I work with in standardization on a regular basis, think that's still true. Oh, they're too complicated. Our people can't learn them. Too much effort. Too much cost. And people on the other side will say, well, nothing is quite as expensive as an accident. And there's a lot of truth in that. But we've been having this argument now for almost half a century. It's a long time. I've been having that argument personally in standardization committee meetings every few weeks for the last 8 years. So it's still there. Meanwhile, Altran UK built this air traffic management system for the UK navigation service provider, NATS, called IFACTS. It's a prediction system. It's a conflict prediction and management system. It is built according to formal methods which they've developed. They do co-static analysis of the code as is being written, and they do possibly daily updates on that code. And they have 150,000 proof obligations that come from the static analysis they do on that code. And every time they do an update, which could be daily, they rerun the prover that discharges those proof obligations on those 150,000 proof obligations, and it takes them about 10 minutes to 50, normally between a minute and 10 minutes, but it can take them up to 15 minutes on a desktop computer. That is a trivial amount of resource for what I would claim is a very well-developed program. That's where we are. That couldn't be done when Barry Beam said formal methods don't work, but that was a long time ago. But people are still saying that. There's a lot you can do. Here is why you should do it. I'm going to use the example of requirements quite a lot in this talk. I'll keep coming back to it. There are many aspects of dealing with software and various aspects of software, but requirements is particularly sensitive. And here are examples that Michael Jackson pointed out in 2012 in a paper he wrote for the Festschrift of Martin Glintz. Matt Heimdall, Steve Miller, Alan Tribble, Michael Whalen showed in, it was a bit earlier than 2006, but they did an analysis of a mode control for flight guidance system. This was a flight guidance system for a pilot-controlled airplane. This was not an automatic piece of space junk or future space junk, which is what Alan Tribble has done a lot of work with. And the original requirements were expressed in natural language as statements with shall in them. This shall be the case. This shall be the case. So the idea is obligation. When somebody says shall, they have an obligation to make sure that what is said after the shall actually happens. And they reformalize that in a form of temporal logic called CTL, which comes with a model checker, or comes with lots of model checkers, I should say. They formalized all the shall statements in CTL, and they ran their model checker on it. And what we might want to think about the requirements is that they cover all of the situations the system is going to be in. That is what I call completeness. Some people object to that word. In particular, they object to that word because a lot of other people will say, you can never show your requirements are complete. And if you can never show it, it can't be a good thing for requirements to be. But in fact, it's the most important characteristic of requirements, that you have covered all of the situations that your system can be in. Were they unambiguous? Were they consistent? And as Michael pointed out, inevitably, they were not. So let's have a look at one case. There was a fairly well-validated and non-controversial requirement in this stack of requirements. If heading mode select is on, heading mode means that the airplane is going to follow a particular heading given by wherever you set the heading. So fly this heading of 350 degrees. That's the heading mode selector. And heading select mode shall be selected when the heading switch is pressed on the flight control panel. I'd look at that, every other pilot would look at that and say, sure. But there are errors with that if you're writing them as a set of requirements for a system with a set of modes. The event of pressing the heading switch can actually be preempted by a higher priority task. So there are cases when you would do that, and it would be preempted, in which case, hopefully, you'd be told that your pressing of the heading switch hadn't worked, or something would happen. But anyway, the requirement was missing. If the requirement is missing, nobody's going to do anything about it. Secondly, you shouldn't let the pilot on the side which is not active in control press the heading switch on the autopilot. It has to be performed by the pilot piloting the aircraft. That was a requirement that everybody had just assumed, and it wasn't there. So this paper was published 12 years ago. Are we better? Well, I'm not sure, but let's go a bit further back. This is David Harrell talking to somebody about the requirements for a chemical process plant. And I won't go through the details, but I hope you can see that those 3 requirements there are not necessarily identical. They are all different. They're not necessarily contradictory, but they are certainly not unambiguous. They are, as we would say, ambiguous. Harrell's partial solution was state charts. That was a longer time ago than 2006. Are we any better? Well, let me tell you what happened to me last month. I went to one of the 2 big German industrial safety conferences. One is put on by TÜV Rheinland in Cologne, and the other is put on by TÜV Süd in Munich. And this is at TÜV Süd. And there was an engineer from a very well-regarded critical software company talking about what they did with agile methods, because there is a separate issue in safety that agile methods don't lead you to the kinds of documentation and assurance that you need for developing systems according to 61508. Other people say, well, actually, yes, they do. You just have to put things together in a different way. So here was somebody talking about how their company uses agile methods to design what could be safety-critical software. Very, very fine-grained. Their teams put together builds multiple times a day, and these builds are looked at by multiple other inspection teams that day. So extremely fine-grained control on very minor modifications, and they have a lot of success with it. It was very impressive. It was a reminder to me that, and to other people, I hope, that traditional waterfall and V-model methods are mainly about how you structure the documentation, how you structure the reasoning about your system to show to an assessor that that system is really as safe as it needs to be. So he stopped his talk, very impressive, and I said, okay, what about your functional requirements? Everybody knows that, you know, the intermediate stuff can be put together in various different ways, but what do you do about requirements? You haven't said a word. And he then said something about, he told a story about, well, we get the user stories and we do something about it. User stories, what are these? They are discursive things written by people on A4 sheets of paper in natural language. That's all they are. There are no checks. They're not even use cases. You don't even have to say, what are the objects here? How do they interact? There's no structure to them at all. So they're putting a very highly sophisticated software development practice, which involves extremely fine-grained coordination amongst multiple coders and inspection teams, on top of fairy tales, as far as we know. We don't know what's in those user stories. This is not 15 years ago. This is not even 20 years ago. It's today. It's what I was told at a conference a month ago. So standards are supposed to handle this. What do the standards say? Well, let's go back to what the standard says. The standard says for the selection of appropriate techniques and measures to put together your software safety requirements specification. Software safety requirements specification. That's a long phrase with 4 words in it. It should be complete with respect to the safety needs to be addressed by software. Okay, so let's be clear, this is not about all requirements, this is just about safety. It doesn't say safety requirements, it says safety needs. What's a safety need? I don't need to tell you that's not defined. Correctness with respect to the same class of safety needs? Well, okay, what does correctness mean? It means at least consistency. Freedom from intrinsic specification faults, including ambiguity. Okay, so we know they have got to be unambiguous. Good. That could be constituted as part of correctness, but it's obviously not. They should be understandable. There should be freedom from adverse interference from non-safety functions. Well, sure. And they should be capable of providing a basis for verification and validation. It doesn't say they should be verifiable and validifiable. It says they should be capable of providing a basis for, not that the basis actually exists. Well, just to make things clearer, we're talking about a software safety requirement specification. So let's take the first 3 words of that, and let's look at software safety requirements. Are they defined? No, they are not. There is an entire section of this standard consisting of definitions. That's all it's got in it, and they are not defined. But in part 1, overall safety requirements are defined. A set of necessary overall safety functions shall be developed, and these shall constitute the specification for the overall safety functions requirements. Okay, so we have an overall safety function requirement specification. Well, that's on the way. And security threats have been identified, then a vulnerability analysis should be undertaken. Okay, out of the middle of nowhere, in your overall safety requirements, it says you should do a security analysis. Well, okay. Then for each overall safety functions are what we get from, let me read it again, overall safety function, what? Overall safety functions requirements. There we go. So safety functions are what come out of that. And for every safety function, you have a target safety integrity requirement. And the overall safety integrity requirements are the target safety integrity requirements for the safety functions. Got that? On to the next slide. There will be a quiz at the end. Safety requirements, this is a summary. This is my attempt at a summary. Please understand I have read these many times because I'm actually on the maintenance team for both parts of this standard. So when I appear puzzled, sometimes I am genuinely puzzled, sometimes it is merely ironic. Safety requirements essentially consist of what safety functions there are to be. Safety functions are things explicitly put in to avoid or mitigate unacceptable risks. So the standard is risk-based. The hazard and risk analysis has identified unacceptable risks, and the way you deal with those is you try to avoid them. If not, you build a safety function which will avoid them or mitigate them. And those safety functions are the things that get safety integrity requirements. And the safety integrity requirements for the safety functions that you have identified, that is the safety requirements. That's the basic idea of this mishmash of words. And a safety integrity requirement is, in fact, specified in the definitions part under, not under safety integrity requirement, but under safety integrity level, where a note says, oh, by the way, these are safety integrity requirements. What is a safety integrity level? It is a reliability requirement on a safety function. So, safety requirements and software safety requirements come from identifying safety functions. Those safety functions are the overall safety function requirements, and then they get a reliability requirement per safety function, and that is then the safety requirement specification, the list of safety functions along with their reliability requirements, otherwise known as a safety integrity level. So safety integrity is actually a reliability requirement on a safety function. But now we come to software. The problem with the safety integrity levels is they are defined in part 1 for what are called random dangerous failures, as opposed to systematic dangerous failures. And for random dangerous failures, there is the table of reliability requirements. They say you're allowed 1 dangerous failure every so many demands or every so many hours of operating. And they get much more stringent. We'll see how stringent they get. For software, that is generally regarded as inappropriate because people don't think you can quantify software that way. It is certainly true that most people I have met in software engineering cannot quantify the reliability of the software they're building in any statistically valid way. So it seems to be a good idea that we don't try to do that if most people can't do it. So what you get for software is a software systematic capability instead of, well, the software inherits a safety integrity level. It doesn't get a safety integrity level because the only thing that gets that is the safety function. The safety function is something abstract. But a safety function must include hardware because code sitting by itself on a piece of paper does nothing. Code sitting by itself in a computer memory does nothing. It's only when the code is executed that something happens. And for the code to be executed, you need hardware. And a safety function is a function. That is, it is something which gets something to happen. It's not a piece of documentation. So since a safety function is an action, or is a function which engages in actions, in order to get those actions, you do need the hardware. So the safety integrity level comes on the hardware, even though software might be a part of that. If you put the hardware and software together, you need a word for that, and the word is element. But unfortunately, it's not a very well understood concept. Despite the fact the standard has been there for 20 years, we had an official query to the German National Committee for 61508 3 months ago, asking what an element was. A reply was given. I won't say that the recipient got a reply. I should say a response was given. Okay, so what happens with software? It's got a systematic capability. As you might imagine, the systematic capability should be aligned with the safety integrity level of the safety function, but that is a reliability requirement, a statistical reliability requirement, which can't be imposed on software. So what do you have to do with software? Well, you have software safety requirements. We've seen you have software safety requirements. We've seen you should have a software safety requirement specification, but we don't yet know what it is. So software safety requirements specify, they must specify the safety function, and no longer, do I have it there? Yes. I should point it out. Systematic capability, remember I said software gets a systematic capability rather than an integrity level. And systematic capability is a measure of the confidence that the systematic safety integrity of an element meets the requirements of the specified SIL. So although you're talking about software, it's talking about the element. So it's also talking about the hardware on which the software runs, maybe. And it's not talking anymore about your software shall be reliable. It's talking about a confidence that the stuff shall run right. So software systematic capability. I'm 20% confident that this software won't fail in the next hour. That is a software systematic capability. Or I am 15% confident. That's what we're talking about here. But that is the software safety requirement. So what it gets is you have to list the safety functions that your software implements or partly implements, along with the confidence that you think it's right. 20%, 60%, 80%? Not specified. But if you have that, it's a software safety requirement. I'm 2% confident that this software written by the students in my safety course is going to work in your nuclear power station. That's fine. What actually happens is there is a list of things you're supposed to do to software. And the list of things you're supposed to do with software is in a big set of tables, and it says if you have a lower integrity level, you're recommended to do this, or we're expecting to see this. And if you have higher integrity levels, you're expected to see this or do this. And indeed, formal methods are highly recommended for the upper two safety levels. Highly recommended is the highest it gets in terms of insistence. You can get recommended, or you can get highly recommended, or you can get not recommended occasionally. So highly recommended is
mandatory, Peter. There's some mandatories.
This is not, highly recommended is not mandatory.
I know, but there are some mandatories in the standard unless they got removed.
But not in the tables where they say what you're supposed to do with software. This is a list of methods like functional block diagrams, and so they have a list of these methods. And according to these methods, you may or may not apply. There are mandatories. But according to these methods, highly recommended is the highest that you get. So much for formal methods don't work. So Barry Beam said formal methods don't work. Here, and that was only 10 years after Beam said that, they were highly recommended for SIL 3 and SIL 4, which means you pretty much have to do it. When it says highly recommended, it means if you don't do it, your assessor is going to want to know why. So you have to have alternatives for showing that you could do what the formal methods could do. But the problem is, nobody says what formal methods are. And we have already seen the way that is implemented, namely user stories. So what to do about all this? It should be the case that requirement specification is not that hard. And safety requirement specification should be a subset of requirement specification. Now, I imagine those of you who have not seen this before could not necessarily pass a test on everything that I've just said. That's how complicated it is. Remember at the beginning, though, the standard says they should be understandable. So what did we do? Back in 2009 to 2011, I sat down with a bunch of my colleagues, and I said, there've got to be certain points here where we can say, this has to be shown, 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 if you're developing software. And we identified 26 of these points. That's why I call them assurance points, and that's why I want to say it's a technical term. Some are objects. We say a functional requirement specification should exist. Not only do we say that, we say a functional safety requirements specification should exist. So we have those things. Those things need to be there, and they need to exist. We can hope that those terms will be defined. And some are arguments showing properties and relations between these objects. For example, you can have an argument that the design spec fulfills the functional requirement spec. Where here fulfills is a binary relation between two specifications. If those two specifications are in some sense formal, you can expect that binary relation to be formal and algorithmically checkable. And indeed, in many cases, it is. In the case of the systems that Altron UK put together, they are very, very concerned to make that relation fulfill as formal as possible and as algorithmic as possible. And they can tell you exactly what they do to do that. So let me run through these 26 in 2 slides very quickly so that you can just get a flavor of what they are. I'm not going to talk about them in detail because the spirit is what is important here, not the detail. There's got to be a formal functional requirement specification. There's got to be formal analysis of it. You have to have a safety requirement specification. That has to be analyzed. What does analyzed mean? Consistency, completeness, etc. We want some kind of automated proving or proof checking of properties. You can certainly do that. We've seen that Heimdall and company could do that on mode controls for flight guidance systems back over a decade ago. That should be routine. It's not. Formal modeling, model checking, model exploration. A formal design specification and its analysis, again, automated proving and proof checking of fulfillment of the requirements by the design. There we are, number 9. That's what I just mentioned in the last slide. The usual stuff, model explanation, model checking, formal modeling of the design, formal deterministic static analysis of the design according to information flow and data flow and possibilities of runtime error. That is done by many companies at the moment. We have a company called Absent in Germany that does that and supplies tools to the people, ADSYS, the people that provide SCADE to Airbus. And SCADE is used for DAL-A critical systems on the Airbus 380 and various Airbus helicopters and various other Airbus flight control systems. So this is quite mature technology being used in the most critical systems, in the most reliable critical systems industry on the face of this earth by people using formal methods. There is something called an ESCL, that's just source code. Let me say nothing more about that. Source code should have a rigorous semantics. It should also be possible to automate verification condition generation from your source code. So if you're using C, you already have a lot in front of you. But there are tools that can help you with that. They do that by giving formal restricted semantics to C and cutting out that stuff which is ambiguous and all of the other kinds of things that have been applied to Ada and various other languages by other people. They make the languages more appropriate. We have a list of things you can generate your formal tests from. There's formal coding standards analysis, there's worst case execution time analysis, and last but not least, runtime verification. Building in tools for runtime verification that the system is still operating correctly. So that's a list of the things that can be done that are currently industrially mature. They were industrially mature when we wrote them back in 2010. 8 years later, they are still industrially mature. Nothing has gone backwards. They can be done. So we suggested that there should be a standard which says, these are the kinds of things we expect if you're going to write software that is going to be dependable. These are things that are done, but there is no standard which says, these are things which could be done. These are things which should be done. So I started working on this with the Safe Software Working Group of the German National Committee in 2010, and 8 years later, we got a document forwarded to the IEC. It's currently out for voting. So there is a document which says, we're writing a technical specification. Here are these 26 assurance points. Here are the techniques that you can use at these points for assurance. It won't say more than that, but the point about a technical specification that comes out from the IEC is that is then a standard which says, these are assurance points in software. At that point, people writing software that is supposed to conform to 61508 Part 3 will have to pay attention to that. Because if they don't pay attention to that and something goes wrong, somebody's going to end up in court, or the regulator is going to end up saying, there's this document, there's this standard which says there are 26 assurance points here. Where are they in your software? And if you don't have them, then you're in trouble. That is the force of writing this as a technical specification for a standard. So stepping back for a moment, what is the motivation behind this? The motivation behind this is to get methods which have been shown to lead to more reliable software involved, in place, in the software industry that is writing and designing safety-critical software. The moral question is, should we now be building systems that we can't guarantee are fit for purpose? When you take a drive in your car, and a wheel falls off a few hours after you've taken it out of the showroom, you don't think, oh, well, that happens. There's risk involved with driving the car. You say, the wheel fell off. And if somebody isn't found to have done something bad, there will be a recall. There's a whole process in place for saying we don't even allow one of these things to happen. That's what happens in aerospace. Aerospace says you should assure and design your systems according to a certain set of risks, which we specify. But in fact, the regulations are absolute. It says your airplane shall do this. And if it doesn't do that, the airplane is taken out of services. The airworthiness criteria, the airworthiness certification is withdrawn, and you can't fly the airplane. And this has almost happened on a couple of occasions because of electronic problems, problems with digital electronic equipment on the airplanes. And that's not what exists in the 61508 standard, because that's a matter of regulation. And 61508 is a standard, not a regulation. It can't be a regulation because it is not national. Only national, legally authorized organizations can be regulators. And the standard is not that. Does it still cost too much for the benefit? Well, it depends. This is the point about cybersecurity. If this really is a game changer, if Ukraine really cannot any longer expect to run its electricity supply because it is constantly being hacked and it can't defend against them, then the question is, we're not building that system with a guarantee that it's fit for purpose because it ain't operating, it's constantly hacked. We need to build these systems better, and for these, the insurance points are important. And the engineering economics question, why is this needed? I've just said, many of my colleagues think cybersecurity is a game changer. So what do we really want to do with software? Safety is about not what we want the system to do, but what we want the system not to do. That not is very important. Because in the software part, it says, testing shall be the main validation method for software. Almost 20 of the almost 60 documentation requirements for software that you have to produce if you're building it according to 61508 concern testing and what testing you did. The problem with that is that testing shows the presence but not the absence of bugs. That was said almost 50 years ago by Idster Dijkstra. We're talking about absence of unsafe behavior. And testing can't show the absence of unsafe behavior, as was already known 50 years ago. So, maybe you just want some kind of assurance. Let's take a criterion from aerospace. Phenomena that are not expected to occur in the system lifetime. By the system lifetime, they mean the total accumulated hours of every airplane flying in the fleet until the airplane is withdrawn. That's what they mean by system lifetime. All occurrences of the system running until they're not running anymore. And if you want a phenomenon not to occur in that, that is under 50% chance that it's going to occur when you're running the system, to do it statistically, you would need, for 95% confidence, 3 times the system lifetime of experience. And if you wanted 99% confidence, a little bit higher, you'd need 4.6 times the system lifetime. Just let me point out that if you can't have more than 1 times the system lifetime. That's the definition of system lifetime. You can't do this statistically. So, testing or operational experience is not going to help you here. The core of an ideal safety standard determines what we don't want the system to do. We call those accidents. Accidents have damage associated with them. We want to do that as completely as possible. We want to provide insurance. We have everything. We want to try to determine how it could happen. Precursors of accidents are a thing called hazards, so we want to identify all hazards as completely as possible. If we go too far, that's okay. We're not saying hazards are unique. You may have different ways of slicing the world up, but they need to cover every possible accident that could occur. And then we need to apportion the behavior we call hazards to various system components and say what the system component should have to do in order that those hazards should be avoided or mitigated. That's what we want to do, and software is not exempt for that. Back to requirements. What is going to follow from that general scheme of how we are going to assess the safety systems, how we are going to assure the safety systems? Requirements should be specified, point number one. They should be consistent, because if they're not consistent, they cannot be fulfilled. And as we've seen from the example of Michael Jackson, and Michael has lots more examples over his almost 3/4 of a century of looking at this stuff. And they should be complete. Complete is a bad word. It's one of my favorite words. They should be complete. At least one should try to get them as complete as possible. What does complete mean? Well, one meaning of complete to the theoreticians means an exact specification of which behaviors are acceptable and which not. This is not possible because you can't enumerate all system behaviors. There are way too few atoms in the universe to be able to do that for even the simplest systems. Another meaning is you consider all the circumstances in which the system is going to operate and specify its behavior in these circumstances. So that's a much more practical. And a third meaning, which is that you can define a user-specific, limited view of the system. You look at the system in a certain way, and you can assure, according to the view which you're taking of that system, that you've covered everything with that view. This is actually a very useful way in which formal methods can be brought in to assure certain kinds of relative completeness of requirements. But the second meaning is the practical meaning. And it is the source of most complex critical system failures. This was already known 25 years ago. Robin Lutz said that safety-related software errors are shown to arise most commonly from discrepancies between the documented requirement specifications and what is actually needed for the system to function in the environment in which it finds itself. In other words, lack of completeness of requirements. You've got the requirements, they were written down, your system actually encountered a set of circumstances which weren't covered. That accounted for 198 out of 200 NASA mission failures that Lutz was analyzing at the time. So the overwhelming proportion of errors. Verification means you've built the system right, according to a lot of software people. That is, the machine code fulfills the source code semantics, your source code semantics fulfills the design, design fulfills the functional requirements. Verification does that. Validation, turn two words around in English, you've built the right system. Your functional requirements are complete. You've got all of the stuff your system is going to operate in, and you know how it should operate. The absence of the Lutz phenomenon. You've got everything, not like these 198 cases out of 200 failures that Robin Lutz analyzed. And they're correct, the Jackson examples. I do point out that in some areas of digital systems, they use these words backwards. That is, verification means checking you built the right system, and validation means checking your system is right. But I'm not going to dwell on that. I'm going to go to 61508 definition. Confirmation by examination and provision of objective evidence that the requirements have been fulfilled. Requirements. Which set of requirements? Well, any of them, all of them. Analysis you can use, mathematical reasoning you can use, tests you can use. And verification activities include all of those things, but there is no suggestion at any point that you should maybe conduct static analysis. And there is no suggestion that your verification activities should proceed into operational maintenance of the system, as Altran does regularly. Validation, something completely different. Confirmation by examination and provision of objective evidence that the particular requirements for a specific intended use are fulfilled. And if you're very observant, you will notice there are two different fonts here. There's the italic font and there's the sans serif font. And if you take out those 5 words, you have exactly the same sequence of words as in the definition of verification. So spot the difference. Validation is verification for a specific intended use. That is literally so, according to this. Does that make sense? Does that say what I said when I explained what verification and validation were? Well, just let me point out that neither of these definitions address the Lutz phenomenon. The Lutz phenomenon is the discrepancy between operational circumstances and requirement specification, and both of these are speaking about requirements being fulfilled. So they can't address the Lutz phenomenon. 61508, 25 years after Lutz and various other people pointed this out, has no clue and nothing in it on how to address the phenomenon that she pointed out. I think that's appalling. I think we can do better. How can we do better? I'll take the waterfall model. Waterfall model says you've got requirements, you have design, you have source code, and you have a bunch of other stuff. What's wrong with it? Nothing is wrong with it as an organization of a sequence of stages which is documented. As a software development method, everybody knows and has known for many years that it doesn't quite work like that. But that's okay. We have functional requirements, development and specification. We have design. We have code. And we have object code. It's possible to use mature mathematical methods to assess the properties of the software and its documentation in all of this. And I have left out testing and maintenance, not because I don't think they're important, but because I've just left them out. Functional requirements. That's a list of the things that I've said. Design. You can check a design for you can check a formal specification of a design for consistency. You can also check it for implementability, for information flow analysis, for example, which is what Altran and various other people do. You can check that the info can actually go through your system in the way it was intended. You can compare the design against requirements. Does it formally implement? Does it fulfill the requirement specification? From the design, you can generate your source code, and you can ask, does the source code refine the formal design specification? Key here are the supply chain issues. Nobody writing source code writes every bit of source code. Everybody uses libraries. Very often, companies use stocks of libraries they've built up themselves. Very often, they use libraries built up by somebody else. There is a real issue of supply chain assurance here. With the source code, you need to check the source code implements the design, fulfills the design, in some sense. And if you have different source code levels, for example, if you're writing in Java, you can have Java source, and you can have Java bytecode. You may need to split the verification up into those levels. Making things into smaller steps is very often better. Once you've got that, you generate object code from them, and you have to ask further, does the object code refine the source code? And once you've done all that, you can consider various other things, such as coding standards analysis, worst-case execution time, and runtime monitoring. Now, just to point out, that is the motivation behind the 26 assurance points. The 26 assurance points are particular points in that, but generally, I don't think there is anything in here about which people should be complaining at the moment. In fact, most companies attempt to do some of that. They just don't necessarily do it as well as it could be done. And as I pointed out, I've not addressed testing. Despite what the standard says, it is primary for validation, or expressed in the standards terms, it has primacy for validation. As a native English speaker, I wouldn't necessarily say that. But anyway, I'm not going to talk about testing. So there we are. There's the vulnerability not exploited. Me in my natural environment as I prefer to be. I should acknowledge the support of the German Federal Ministry for something or other. They've given us quite a lot of money to look at all of these terms and definitions, and that's me done. Thank you, Martin.
Thank you very much, Peter. So you have set the tone for the conference. We do have time for a couple of questions. But we also have a coffee break coming up. And but before we go there, I would like to thank you very much, Peter.
Thank you, Martin.
Hand over a little gift. It is our traditional ISIS Applied Cyber Physical Systems exercise that some of you may be familiar with. It is a good complement to cycling. Good luck.
Thank you very much. Thank you.
And before